because sometimes we make a multiple cuts to achieve the shaded area, so we have to be careful about the shear flow issues. So let me use the square box as one example, and then we can also have so this dimension is 12. And those one has the thickness equal to 3. Okay, so on each side that is 3. And so for example here the V is given. So V given in the vertical directions, and then we know that neutral axis should be passing to the centroid of the cross section. Neutral axis is normal to the direction of the V. And that is the first step to identify the neutral axis. Okay, and now using this cross section, I'm going to make a few cuts and to study the distribution of the shear stress across the whole levels of here. So the first one is I want to calculate the first one I want to calculate is the maximum shear flow. Okay, the maximum shear flow. The maximum shear flow, and again, the concept of the shear flow by definition, by our per our formula, is this equation. So the shear flow also involves the Q. So the maximum shear flow for this case is this. The first one, the Q maximum. Okay, I want to calculate this one. So where is Q maximum? So for this case here, the V is given, and I here I equal to 112 and 12 Q minus 112 6 Q. Okay, so this one we leave it. I don't have calculations. So V is fixed, I is fixed. To calculate the Q maximum, that is a place where they can give us the maximum value of the Q. Where is that cut that can give us the maximum value of Q?
Neutral. At the top?
Huh?
Neutral axis.
Neutral axis, at the middle, right at the middle here. Okay, so that one, let me draw this one again. Here. So this corresponding this shaded area will give us the maximum Q, and that corresponding will give us the maximum this one. So for this area, that will this. Okay. So that means the maximum shear flow. For example, if this is the half, I don't have column, I just make a half. But here, you imagine here should have another one. So the maximum happens just at the middle cut here, at the middle cut at this level. That is the maximum shear stress happen here. Corresponding is the maximum Q is half of. Corresponding is half of this cross section. Based upon the half of the cross section, we calculate for Q. Are we okay? Any questions? Okay, we proceed. So for this case,
do you want to maximize the area? Is that why?
Yes,
okay.
Because you can see, because this formula, Q equal to VQ over I. To find the maximum Q, under the V constant, I constant, we looking for Q where is maximum.
And so you're going to get that when the area is the biggest.
So here, yeah, so here that will be give us the maximum. Okay, so here we can calculate Q. For this case, we given our dimensions here. So here is, we can put into, say, the 3 range. 1, 2, 3. So here is 3, 6, 6, 6, 3, 6. And then this is the centroid of the one. This is the centroid of this one. This is the centroid of the other one. So for this case, the Q maximum will be equal to the three pieces together. 3 times 6, and I calculate this area first, and then this is 3. Okay, so times 3, and this one, we have the two portions, the identical, so multiply by 2. And now I work on the middle one. The middle one, the area is 6 by 3. And then from here to here, the distance here is 4.5. So here the Q maximum is 189. So therefore, dq over I, that will give us, for example, let me designate, say on each side, this is the Q, and on this side, this is a Q, and here, let me say there's a Q maximum here. Okay, so here I say on each side, the shear flow is Q. So per my notation, I designate each side, the shear flow on each side is Q maximum. So here, for this case, this is 2 Q maximum, right? Will be equal to V over I times 189. Because my 189 is based upon the two cuts. So that means the produced information should be going to the two sides. Are we okay?
So why you multiply by 2?
Because again, this one is based upon the shaded area. The shaded area involves the two cuts, which means involve the shear flow underneath. So 2. So that suppose I should be, for example, here if you can write this is a Q maximum. This is this side plus this is this side. Okay. So for this case, we know for each side equal to 94.5 V over I. So we take it. So here let me label it. So along this side, the Q here equal to V over I times 94.5. Okay, we label it the same. On the other side, this formulation is this plus this. That is 4. Okay, we continue. And the next one I want to find is the Q here, and for example here, along this cut. Okay, and that distance, for example, if this is a center line, and say I give a parameter, say S. So I want to calculate the shear flow in this cut. So let me do, I have to erase this part, but okay? So for the second one, again, let me draw the whole entire cross section. Neutral axis. This is a center line. And now we make the cut is here. Okay. And again, we try to utilize these equations. For this equation, Q corresponding to is the shaded area. So the strategy is this. Because we already know the Q here. V over I. then if I would pick this shaded area for Q, then our equation Q equal to VQ over I, and VI given Q are corresponding to this shaded area. And this Q representing is the total shear flows on the cuts we make. For this case is this one. Let me call QS. And this one. So this one is QS plus Q. This one is QS plus this portion.
If this wasn't a square, would this hold true?
Say that again.
If QS was greater than what this distance is, would that
That's
be
always
true?
true. Always true. Okay. So again, this equation tells us is the shear flows corresponding to that is the cuts making for Q. And for this case, we have two cuts here, one cut and one cut. That representing is the area. Right now I'm talking is in this case. We make two cuts. In concept, it's like this one. We make two cuts, Q1, Q2. Okay, and then we calculate our Q, the capital Q, based upon this area, respect to the neutral axis, right? So basically that representing, again, concept is this. We are looking for is to calculate what is the shear force, H here and H here, H1 or H2. In terms of the unit length, if this is the unit length, then that means Q1 and Q2. Again, Q is the shear force per unit length. So basically here we're looking for, I'm solving for is what is the force here and what is the force here. And once we select this area, for example like this, then we have the total shear force, and that is the two parts here. And because here we have already this being calculated so easily, we can solve for QS should be equal to this value. Let me calculate this value quickly. For that case. So if this is say if this is the dimension, the distance from the center line is S here, then quickly we do the calculation. Let me skip the detail, but that will give us is 94.5 minus 4.5 as this is for Q. V divided by I. Okay, so if you do the careful calculation, this is 4.5 S. Okay, based upon this simple geometry, you should be able to get that number. So therefore, we can solve for QS. We simply do the information, the QS will be equal to VI minus 4.5 S. For this beam, yes.
Are you not going over the calculations because it's supposed to be simple?
Because,
Or like just because of time?
yes,
Or-
because of time. But this calculation is easy. If you can say, for example, here, you can put into two regions.
Mhm.
And this will be 6, this will be 3. And this one will be 3 minus S, right?
Okay.
So easily you can get
So you
that.
have 3 sections?
Yeah. So now we got this QS. So which means right now, for example, let me use this as the for illustration. So that means here on one side we have the Q for this case, and on this side we have the Q for this one. Are we okay? Right now we're calculating this the shear flow representing is the force here per unit length. This is unit length. Okay, remember here is a force per unit length. Basically, that's a force. So once we have those numbers, Q, and then simply we divide corresponding Q. We divide the Q with corresponding to the thickness. For example, if this is a Q here, divided by this thickness, that will give us the shear stress. And Q here, divided by this thickness, will give us the shear stress. Okay? And now the question I'm going to ask is, here for this Q, that is positive 94.5 V over I. If this is a climb, and if we have a bending like this, so the shear force, if this is a climb, if we have bending like this, the shear force will go that direction. The same thing, the climb here, the shear force on the two sides, positive will go that direction. So that is the way the sign will tell us the direction. So here is negative, that means on this side, the shear flow, the shear force is going toward me. At the bottom side, the shear force or shear flow going toward you as the positive, and negative meaning toward me. Okay. And anyhow, so that means here let me draw the direction. So with this as the cube. Right now I want to draw the shaded area into 3D viewpoint, and for better viewing of the direction of the shear flow. What's interesting will be okay, so now I expose is the area along this cut and area along this cut here. Okay, so that is here and here. And the Q, this one, is going out, and that is 94.5 V over I. And this one with the negative, that means that is going in that direction. Okay, simply direction, give their sign. So corresponding the shear flow, right now I'm converting all the information. This is part of our cross section. So that one is part of our cross section here. So let me okay. So that is part of our cross section. So part of our cross section, you can see if the shear. So say if this is the so if Q equal to this one, then tau will be equal to Q divided by T. And say here that this is the T here, equal to 3. So that would be equal to 94.5 V over I divided by thickness 3. So that is our tau. So for this case, the tau calculated basically here at the bottom here, the tau is in this direction. So on this side, the tau will be in this direction. In a similar way, if we have the Q on this side equal to this, so corresponding the shear stress equal to Q divided by, again, thickness. For example, here the thickness, again, equal to 3. So that is equal to 4.5 S divided by 3 V over I, and that is 1.5 S V over I. Again, so now the shear stress corresponding is in this direction. So on this plane, the shear stress will be here. So on the entire cross section,